All right, welcome to today's tutorial. In today's tutorial, we're going to be talking about Euler deconvolution. We are going to be doing Euler deconvolution using both standard Euler deconvolution and located Euler deconvolution. So at the end of this video, you should be able to know how to run these processes. You should be able to know why you are going to choose different parameters and what makes it good and how to properly window your results at the end of the day. So my name is Dr. Jude Jepu and you are welcome to today's tutorial. So let us just cut right into the chase. For the image that you are seeing right here, I will tell you that a long process has been done for us to get here. If you want to know how we have done this, please check out our other videos to learn how these things have been done. But suffice it to say that I have done reduce to pole using the differential reduce to pole method on this particular data. We have done upward continuation using 125 meters. That is related to the just one cell size, because the cell size grading method for this particular thing used a cell size of 125 meters. And at the end of the day, we did regional residual separation. So what you are seeing here is the residual component of this magnetic data. Also, another additional information, this data was acquired at a flight line spacing of 500 meters, and that's why we chose a quarter of that spacing to use for our grading. Mind you, we use the minimum curvature grading method, and the sensor mean terrain clearance for this was 80 meters, and this is going to come up when we are choosing the parameters for the Euler 3D deconvolution. So let's start immediately by going to the Euler 3D menu. If you don't have it, go to this GX and click on load menu. You can just search for Euler 3D here, and I'm sure you're going to get it. And once you click open, this menu will pop right out. So you click on here. You see, this Euler 3D model is designed in such a way that you can go through it just stepwise like that. But we have done our grading, so we are going to process our grades. This particular thing, we calculate all the derivatives that we want. You can calculate the derivative on the x-axis, the horizontal derivative on the y, and then the vertical derivative, which is the z. So it automatically populates this, and we are going to use it. And like I said in the previous video, when I explained the fundamentals and the theory behind this Euler deconvolution, you will know why we are using upward continuation. It's just to remove those effects of those the noise that may be in the data, but then care should be taken in order to remove those shallow sources that may just be very essential or important to our project. And then since we have done this already, we can now leave this space blank. But if you have not done it, like I said, I suggest using the spacing of one cell size, and for our cell size here is 125. So if you have not done it, you have maybe chosen to use 125 meters as your upward continuation distance. And then we have this the grid expansion. In the fast Fourier transform, we are using the square method. So we click on OK immediately, and then it computes all these derivatives for us. And now don't freak out when you don't see these the results. You can easily go to this grid here, right click and add grids, and there you can see all these ones, the dx, the dy, and the dz. We can pop them right open, and these are all the grids that have been processed, and we have them here. So let's go back to this menu and go to the standard Euler deconvolution. Like I said, we have both standard and Euler. In order for you to know the differences between these two, I advise again for you to check the previous video that I've made in order for you to get the concept and get some intuition about why and how these are done. And it has populated all these. For the solution database, this is standard. We name it standard Euler database. And for the structural index, again, if you go through the previous video I made, it explains all this. For this one, suffice it to say we're going to be using just one. And for the maximum depth tolerance is 15. And this one will reject any error estimate that's just above this 15% and retain the others. Now, the default is 15%. And if you want fewer depth estimates, you can use lower depth tolerances. And for the window size, And like I said, you have to know your geology, the anomaly that you are seeking for, and an idea of the size of the anomaly. In this case, let us assume that the size of our anomaly is between 1 to 2 kilometers. And in the cell size, since we are using 125, if we use 10, we are looking at 1,250 meters. That is 1.25 kilometers. And remember, we said our anomaly is between 1 and 2 kilometers. Now, our window size should be large enough to take care of all the anomalies that we need. And then it should not be that small that it may miss some of these anomalies. So in order for us to take care of this, we'll use 20. 20 times 125 will give us 2.5 kilometers, and that is an average of what we really need. Like, again, Euler deconvolution is an iterative process. You can continue doing it and test and see which one works best. But suffice it to say, for the purpose of this tutorial, that is what we are going to be doing. And the maximum distance to accept, usually by rule of thumb, we are using half the size of the distance, and half size of 2,500 is 1,250. So the maximum distance to accept will be 1,250 meters. And like I said earlier at the beginning of the video, the sensor mean terrain clearance, or the flight height, was 80 meters. So we put 80 meters here and we click on OK. So it will compute and bring out the Euler solution for us. In order for us to save a lot of time in this video, I'm going to pause and wait for it to complete. Okay, so now it has finished and we have our solutions here. And if you go again, I will keep referring you to that particular video because it's actually the first video that I've made in this series, to explain all that we have here. But there's why you say that this is our depth solution. This is the solution that it has calculated. For this x underscore Euler, it gives us the position of the anomaly that we have. For this x offset, it's actually this this x Euler minus this x coordinate here will give us this offset here, and the mask is the ones that are supposed to be plotted and the ones that are not supposed to be plotted. This d gives us the confidence that we have in percentage for the solutions that we have. And because we gave 15%, if you look at the statistics of this one, you will see that it ranges from 1 to 15, and that is what we have chosen to give. So the lesser the amount of the difference here, the percentage, the more confidence we have in the solutions that it has brought. And I have discovered from experience that working on this Euler deconvolution using Oasis montaj for the processing and the visualization of the data kind of takes time. So usually I export this solutions database to a CSV file where I will continue the process in a GIS software. For example, I'll be using ArcGIS Pro, and for this particular purpose. So what we're going to do is that we're going to export this database for the standard Euler deconvolution. All you need to go to is to go to database, click on export as CSV, and we are going to export this database to a CSV file where we are looking at all the database channels and we are looking at all lines. Include dummies? No, we don't want to include dummies, and all these are going to be there. So standard Euler, if you like, even if you don't put the extension, it will still automatically add it. So we are using this standard Euler as CSV. So we have exported this data and we are going to continue the processing in ArcGIS Pro. And for us to continue, we are going to work on the located Euler deconvolution. Again, if you watch the first video that I made, the located Euler deconvolution starts by calculating the analytic signal. So we will calculate the analytic signal here. Here, for you to calculate the analytic signal, you have to have all these three components, and the grid is giving you as as.grid, and it says you have to view, display it in the current map. We just click on OK, and that will pop it up, and we will see the analytics now. Okay, we have not created a new map, and that's why we have this particular issue. But then it is actually doing this on the DZ because we are supposed to create another map before we actually do this, and this is not a very good one. So we'll go back and do the right thing. Let us go back and recalculate our dx, and so that we don't have issues. Let's go to process our grid. Let us reprocess this. It's not going to affect the results that we have here. It's just that we are reprocessing these grids in order for us to get what we actually need. In order to do that, is a part of the problem. Let us delete all this and see. Let's delete all this. Let's delete them. Yes. We just start. It's actually a very fast process. Dx, dy, dz. Let's go there and let us add them again. Add them again. So we are adding dx, dy, dz. Okay, we are in good hands. Okay, come up. Okay, we are back to normal. So in that way, let us kind of create a map for ourselves. We'll create and draw a base map. Okay, no, let's go to map tools, new map. Let's create new map from XY, and let's scan our data. We are scanning the data, and these are the extremes, and we'll go to next. Let's just say the map name is analytic signal. Okay. Landscape letter, let us use A3. The map scale, let us automatically populate it, and let it be this one, and we can say finish. Okay, so we have the analytic signal map, and if we go to map tools, we draw a base map, and okay, let's leave it this way. So when we are calculating this located Euler deconvolution, we are displaying the analytic signal on this current map that we have here. So we are not going to have those error things that are there. So we can actually make this map better than the way it is, but for this purpose of this particular tutorial, this is what we have. It is not the best map in the world, but we can actually make it better. It's just for us to display this data for now. And then we will continue with our processing, and we go to get grid peak locations for this. And we're using the analytic signal as the input. And for this output database now, we will name it located Euler deconvolution. And this is solutions. The channel, we have the grid value as what we are going to get. And others, we just leave them as it is there. We can choose the symbols and all that, but it's not required. So these are the solutions. These are the peaks in the analytic signal that it has shown us. You know, we can of course change these particular symbols. If we do this grid position, we can actually change the symbols from crosses. We can either choose circles but those ones don't really matter for now. So let's cancel and let's go back here, and we'll now do the located Euler deconvolution. So we are still using the original data that we have, which is the residual of this sheet. We are keeping all these. We are using the solutions, locations, and for here, because we have previously done this, all this information were automatically populated, and we click on OK. So it is telling us that it will not find value Euler solutions for one of the 1,467 locations. It's just OK. Now, if you look at this database, it's not showing everything, but you can just right-click and you can say display all. It will show you all that it has done in this place. And the next thing is for us to continue this process in ArcGIS Pro, where we export as CSV, and this time around we name it located Euler deconvolution.csv. We are using the all database channels, all lines, and we're clicking on OK. So for now, we have been able to calculate these solutions, and the next process, we're going to continue that in ArcGIS Pro. You can use any GIS software, but I prefer using ArcGIS Pro. So let us open up ArcGIS Pro and continue this process. Okay, so just before we go to ArcGIS Pro, I want us to explore and look at this data that we have exported. And for the located Euler that we exported, let us see how it is. Okay, so you see that we have all these data sets here. We have, let's see everything that is here. Okay, so um, so we have the grid value, the window size, the marks, the depths, and all that. For now, the most important is the X Euler and the Y Euler. These are the locations for the X-axis and the Y-axis, or the northings, these northings and the eastings that we're going to be plotting. And another important one is the depths, which of course the depth solutions that was derived from running the Euler process. And of course this the Z, because this actually tells us the estimates, the confidence level we have in making these things. So like you remember there we have these values between 1 and 15%. The lesser the number, the more confidence we have. But you're going to be using that for windowing the data, but this just gives you an idea. And a quick look at the data set, we see we have 1,138 here. So, and let us open the standard Euler. Like I said, the located Euler gives smaller solutions using the peak values that were generated using the analytic signal. And for here, we'll see that the standard Euler is actually much larger than the located Euler, where we have solutions of up to 203,700. So like that is a thing that standard Euler does and the located Euler gives you. So you can do the manipulation and the filtering here when you want to window your results in order for you to know which works fine for you. These things are iterative. You can play around with them, do different structural indices, but for now, we are concentrating on just the first process for us to get the results and plot them accordingly. So we're going to be closing this and returning to, I don't want to save, returning to the ArcGIS Pro. Now we are going to be loading our data. So we go to map and add data. We are going to add XY point data, and we are going to go to where we have our data. This is running slow. Open up, man. Okay, we have got it open. So where is the location of our table? And our table will be located. Let us load the standard Euler deconvolution first, and let's also rename it standard Euler. Let's take off all this. And what is the X field? Remember, we are using this X Euler and the Y Euler as the fields. It is in UTM zone 32. Let's not forget that. And okay, we can go to and set some of the environment settings. And let's say we want the output coordinates to be in zone 32 north. Everything seems fine. We click on run. So it will load these data points here for the standard Euler. But while it is running, we can easily rename this to be standard Euler. So we would not be confused when we are working on other things. So the data has been loaded, and this is for the standard Euler. Let us take off this OpenStreetMap off. Let's take it off. Okay. In that part of Nigeria where we have this, just want to make sure I'm using this base map to make sure that we are correctly, okay, we are correctly located where we have this data point. Okay, and let's take this one off. So we have the standard Euler, And then let us do another one for the located Euler. So we do a new map, and let's rename it properties, and let's call it located Euler. So we'll be able to see the differences. Apply. Okay. And for the located Euler, we are going to go here and load located Euler. Located Euler. We're going to load that, and we name it located Euler. Located Euler. And again, let's drop this down to choose the X Euler, and you choose the Y Euler. This thing still remains the same, and we click on run, and that will produce the data for the located Euler. So as it were, we'll see how these things are. This database solution is quite few as compared to the one you have for the standard Euler deconvolution. So the aspect is, if you want to window and all that, we'll come to that. But first of all, let us see if we can display this the way we want to display. So let's go to feature layer here and click on symbology, and we are using the proportional symbol here. Let's see how that one works. And for the proportional symbol, oh no, okay, let us start with the graduated symbol first, and then the field that we're going to be using will be the depth field. We are not normalizing anything, and let us just say let's start with 5 and end up with 50. Of course, you can try different values and see the one that works for you. And then we have about 5 different passes that we are going to have here. I think 50 seems too big. Let's do 25 here. I think that one should be reasonable enough. So we have these depths. So from 62 to this, having these values, and having, but it's not very intuitive using this. And let us color it differently. Let us give it, let's give this color. And let us start from, let's say this is blue. Let's go back and say this one is green. Green. Let's go back and let's say this one is red. Okay, let's say this one, let's leave this one yellow, and let's do this as red. No, not here. Red, and let's go back, and let's use magenta or pink for this, representing higher values. Let's do pink here. Okay, so we have all this symbology here showing the different depth sizes and their solutions. And you can go ahead and make a map for this. You can create a new layout. Let's just say we're using this A3 size, and we are insert layouts. We want to insert this as the map frame. We use this here, and we can zoom to layer here and add some things. Say so this, so we can add the insert. We can insert a grid. We can insert a grid here for this, and we can insert um, the legend that explains the stuff for us here. So this is just a very quick way of doing this. And of course, you can always convert this to graphics and adjust this manually. Instead of having this 62, you can name it the way you want. Maybe instead of having this too many decimal points, you can say this is to 240 and this is from 60 or something like that. But this video will be too long if I continue to do this, but I mean, you'll get the flow of how these things can be. And of course, you can actually change a lot of things here. We can ungroup this and so that we can actually deal with this separately. Group, yeah, so we can actually deal with this. You can change the text size and do pretty much a lot that you can do using some of these things. You can make it bold and all that. So, and this actually gives you what you can do with these depth solutions. And for the standard Euler, let's go back here. We can do something like go to the attribute table, and because we have a large number of solutions here, let us window it and let's just take the DZ, the percentage tolerance levels, I mean the depth estimates that are within between 0 and 5%. Just this is just experimental, but you work on the one that works for you. So for this, we just do on select attributes here, select by attributes. We want to do a new selection. So the field where we're going to is where this DZ is equal to or is greater than or equal to 1. Let us add another clause. It actually populates a number. It's actually start from 1.8. And where this DZ is less than or equal to 5%. No, this is just purely experimental. You can try. 5% is a little bit making it too strict, but then it's experimental. We can click on OK and apply. So this one has selected only those ones that have these values between 0 and 5%. So we can export this data. We can export these features. I can expect as a table. We are using these selected records of 55,000. Even at that, it's still quite high. And the output feature class is, let's say, standard Euler exports. And of course, you can use this filter and you can look at the fields that you want. But then we are accepting everything here. It's still at 55,000. So let us clear this one here. Let us clear it and let us put this in off. So in this case, we are having a much more simpler features here that we can work with for the standard. And then we can, you see, like I said, you can try a lot of things here and we can plot it again using this for this other one. Of course, let us not confuse this. Let us name this layout. Let us name this as the layout for Euler, located Euler, so that we don't get confused. And this is okay. Yes, and this layout here, let us name it general. This is layout for standard Euler. Standard Euler. So what we did was to do that, and we have to insert map frame. We are using this standard Euler map frame and plotting it here. We are using standard Euler. We are plotting it here. So we can say, let's zoom to layer here. Okay. And then we can now do this again by using the graduated symbol, and the field that we want to use is the depth field here. And just like we did the other place, we use 525. I think for all intents and purposes, we're having something like this. And for us to do this one, let's go to making this one like the other place. We're making this blue, going back, we are making this green, green. Which one did we choose then? Okay, let's just use this one. Of course, these are just for practice. You can make it better for yourself. And we are making this red. Of course, there are no hard and fast rules about this. What we are just doing is just to visualize these things and see. And okay, we actually left this one to be yellow then. I think we left this one to be yellow. Okay, let's make it yellow. Now, depending on what works for you, you can just do that. Let's make this one yellow, and this one to be red. Red, and then the last one will be pink or magenta in color. So we're having difficulty loading because of the large database that we have here. But I mean, this gives you an idea of what can be done, and of course how we have been able to window these particular data. So the idea is to try several things and see what works and what doesn't. And at the end of the day, you get your solutions. But I expect you to, it's actually a very long process where you try and retry and make sure something works for you. And I hope this has done it for you. And if you have any question, you're always free to contact me and let us continue to do this. But like I said, the located Euler seemed to give us something of value. But then at the end of the day, you have to know your geology, you have to know what you really want to do, how you want to do them, the anomalies that you're expecting, and probably the depth estimates that you want or you are interested in. I hope this does it. Thank you very much for watching my videos, and goodbye.